The date was March 12th, 1942, and in the sprawling industrial yards of San Diego, California, a quiet crisis was reaching a breaking point. American shipyards were hemorrhaging money, time, and, most critically, aircraft. The Navy needed fighter planes, thousands of them, and they needed them yesterday. But on the factory floor of what was supposed to be America's industrial triumph, the Vought Aircraft Corporation was drowning in its own success. The orders kept coming, the deadlines kept shrinking, and the men building the planes were breaking under pressure that no peacetime manufacturing system had ever been designed to withstand. But then, a man walked into a room and asked a question that would either save the war effort or destroy his career forever. What if we stopped building Corsairs the way we think they should be built and started building them the way they actually need to be built? If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. By the spring of 1942, the Pacific War was a mathematics problem that America was losing in spectacular fashion. Pearl Harbor had been 6 months in the rearview mirror, and the initial shock had given way to cold calculation. The Japanese Navy had the numbers advantage in trained pilots. The Japanese aircraft industry had years of combat experience. American pilots had courage and determination, but they didn't have something that would keep them alive in the brutal arithmetic of air combat. They needed the Corsair. The Vought F4U Corsair was, by any measure, a magnificent aircraft. Its Pratt & Whitney R2800 double wasp engine could push the airframe to over 400 miles per hour. Its inverted gull wing design, that distinctive, almost alien geometry, gave it superior maneuverability compared to earlier Japanese fighters. Its 4.50 caliber machine guns and 420mm cannons made it a flying fortress of firepower. On paper, in the hands of a skilled pilot, a Corsair could turn the tide. But paper didn't win wars, production did. The Navy had placed an order for 8,000 Corsairs. 8,000. A number so large it barely registered as real. Vaught's current production rate, if they optimized every second of labor, if they pushed every worker past fatigue, if they performed manufacturing miracles on schedule, it would deliver 3,500 aircraft by the end of 1944. The Navy needed those 8,000 by the end of 1943. The gap wasn't a problem. It was a catastrophe wearing an accounting label. Manufacturing directors at Vought knew the numbers were impossible. They'd done the calculations 1,000 times, searching for the error that would make the figures suddenly make sense. There was no error. The problem was fundamental. The Corsair wasn't just a complex aircraft. It was a masterpiece of precision engineering that had been designed by men who understood aerodynamics perfectly, but had never designed for mass production. Each airframe required 27,000 individual parts. Each part had to fit within tolerances measured in thousandths of an inch. The wing alone involved more than 800 rivet holes, each one placed by hand, each one inspected by hand, each one critical to structural integrity. The fuselage came together in a sequence that demanded skilled workers who understood not just the steps they were performing, but the logic behind each step. The assembly line at Vought was state-of-the-art for 1940. It was obsolete for 1942. The factory had been designed around a fundamental assumption that production would ramp up gradually, that workers would gain experience, that refinement and optimization would happen naturally over time. War didn't allow time for natural refinement. War demanded immediate, impossible results. Workers were brought in, trained for 8 weeks, and thrown onto a line that moved too fast for them to understand what they were doing. Mistakes cascaded through the assembly process. Wings were attached incorrectly because someone hadn't fully grasped the sequencing. Electrical systems were wired wrong because the documentation was incomplete and confusing. Paint was applied over improperly cleaned surfaces, creating adhesion failures that wouldn't show up until the aircraft was in service. Quality control was a nightmare. Aircraft would come off the line looking complete, only for inspection to reveal that critical components had been installed backward, that welds were incomplete, that structural supports had been fastened with the wrong fastener type. Some aircraft required weeks of rework after they supposedly left the line. The workers themselves were exhausted. 10-hour days, 6 days a week, in a factory that ran hot in summer and cold in winter, with machinery that didn't care how tired you were. Fingers got caught in presses. Backs gave out from repetitive strain. Minds went numb from the monotony combined with the pressure to move faster. The turnover rate was catastrophic. Men would work a month, realize they couldn't keep the pace, and simply walk off the line. New workers would start, learn nothing correctly from workers who were too busy and too tired to teach properly, and make the same mistakes that the previous batch had made. By early 1942, Vought's management was in crisis meetings every single day. They brought in consultants from other aircraft manufacturers. They hired efficiency experts who measured worker movements down to the second. They redesigned workstations. They created new tool racks. They tried everything that manufacturing science knew to do. Nothing worked because the fundamental problem wasn't about workstations or tool organization. It was about the aircraft itself. The Corsair had been engineered without any thought given to how human beings would actually assemble it. The wing struts were positioned in ways that forced workers into awkward angles. The fuselage sections came together in a sequence that required multiple workers to hold parts in place while someone else did the fastening, creating bottlenecks that couldn't be resolved by efficiency alone. The electrical harness was a nightmare of cables that had to be routed through spaces barely large enough for hands to reach through. Every attempt to speed up production ran into a hard ceiling of physical impossibility. The Navy knew the situation was desperate. They sent their own production specialists to Vought. Those specialists looked at the assembly line, did their own calculations, and delivered their own verdict. The current system could not deliver 8,000 aircraft in any time frame that would matter to the war effort. Not even close. What the Navy suggested was radical. They suggested bringing in someone from outside the aircraft industry entirely. Someone from manufacturing. Someone who didn't know what couldn't be done, because they'd never been taught the rules. His name was Marshal Hendricks, and he was an unlikely hero for an aircraft manufacturing crisis. Hendricks was 53 years old, with calloused hands and a mind that worked in 3 dimensions the way other men's minds worked in 2. He'd spent 30 years in heavy equipment manufacturing, most recently as a production manager for a construction vehicle manufacturer in Chicago. He had never designed an aircraft. He had never worked on an aircraft. He had never even flown in an aircraft. What he had done was completely rebuild the production systems for machines that were far more complex than anyone thought possible to mass produce. When the Navy called him in March of 1942, Hendricks didn't fully understand what they were asking him to do. They wanted him to come to San Diego. They wanted him to look at the Corsair production line. They wanted him to tell them if there was any way to produce 8,000 aircraft in 2 years instead of 5. He drove to San Diego in his personal car, stopping at cheap motels and driving through the night because the war effort was urgent and hotels cost money. He arrived at Vought on a Wednesday morning with 1 suitcase and a notebook that was already filled with questions he planned to ask. What he saw on the factory floor made him stop walking. The assembly line looked, to his eye, like organized chaos masquerading as system. Workers moved in predictable patterns, but those patterns were inefficient. Machines sat idle while workers manually performed tasks that could be mechanized. Parts arrived at workstations in batches, creating waves of activity followed by waiting periods. The flow of aircraft through the line was inconsistent, sometimes backed up at certain stations, sometimes creating idle time at others. But more than that, the workers looked broken. Not tired, broken. There was a desperation in their movements, a sense that they were part of a system that was grinding them down. Hendricks watched a young man, couldn't have been more than 25, repeat the same welding motion on airplane frames for 8 straight hours. The worker's hands were shaking with exhaustion. His shoulders were hunched. He was doing the job, doing it correctly, but his entire body was screaming that it couldn't continue. Hendricks spent 3 weeks at Vought without suggesting a single change. He walked the line every day. He talked to workers during their breaks. He asked questions that seemed simple but revealed everything. Why were parts arriving in batches instead of continuously? Why were multiple workers standing around at certain stations? Why did the sequence of assembly seem random instead of logical? Why weren't the workers rotating between tasks? The answers he got were always variations on the same theme. That's how aircraft are built. That's how we've always done it. That's what the engineers designed. Hendricks listened and took notes and said almost nothing. On a Friday afternoon in early April, he met with Vaught's production director, a man named Charles Berkeley, who was carrying the weight of impossible expectations on his shoulders. Berkeley looked at Hendricks with desperate hope mixed with skepticism. Hendricks had been there for 3 weeks and hadn't made any recommendations. Had he simply confirmed what everyone feared, that the goal was impossible? Hendricks opened his notebook and began to talk. "The Corsair isn't the problem," he said. "The way you're thinking about building Corsairs is the problem." Berkeley felt his stomach tighten. He'd heard criticism before. He was tired of criticism. He wanted solutions. "You're building these aircraft like they're custom machines," Hendricks continued. "Like every single airframe is unique and needs individual attention. But they're not unique. They're identical. Thousands of them, all the same specifications, all the same parts, all the same sequence. You need to stop thinking about building aircraft and start thinking about building a production machine that makes aircraft as a byproduct." Berkeley waited for more. This was the kind of abstract philosophy that consultants were always offering. He wanted specifics. He wanted numbers. Hendricks sensed the skepticism. He'd encountered it before with men who were drowning and being offered a lifeline that looked too strange to hold. "I need 3 weeks," Hendricks said. "Full authority to redesign the line. I'll keep your best workers and bring in consultants from outside aircraft manufacturing. We'll modify the assembly sequence. We'll redesign the workstations. We'll mechanize what can be mechanized. We'll create continuous flow instead of batch processing. And at the end of 3 weeks, I'll show you a prototype production system that will produce aircraft at 40% higher throughput than your current line." Berkeley's first response was a laugh. Not a mean laugh, but an exhausted, slightly hysterical laugh. 40% higher? They needed 150% higher. 40% would get them to 5,000 aircraft by the end of 1,944. The Navy needed 8,000 by the end of 1,943. "I know what the Navy needs," Hendricks said quietly. "I'm telling you what we can do first. If you want to reach impossible, you have to get comfortable with things that look impossible along the way." Berkeley made the decision that would alter the trajectory of the war in the Pacific. He gave Hendricks what he asked for. What Hendricks did over the next 3 weeks violated every principle that the aerospace industry held dear. He began by taking the Corsair airframe itself and asking a question that engineers had never asked. What if we didn't care about the best way to build this, and only cared about the fastest way? The engineers at Vought had designed the aircraft for optimal performance in the air. It was brilliant. It was also a nightmare to manufacture. The wing attachments required removing the fuselage from the assembly line, rotating it through multiple positions, and then reinstalling it. The process took hours and required multiple workers to coordinate around each other. Hendricks looked at this sequence and did something radical. He asked if there was any physical reason the wing had to be attached at that particular point in the assembly. The answer, when he pressed the Vought engineers hard enough, was no. There was no physical reason. It was simply the way the design had been conceptualized. Engineers thought about the aircraft as a completed unit and worked backward. Manufacturers, Hendricks understood, had to think about the sequence from first to last and work forward. He redesigned the assembly sequence completely. The fuselage would be assembled horizontally on a moving line, but before anything else happened, the wings would be attached. This required creating new jigs fixtures that held the wings at the correct angle, while the attachment points were fastened. These jigs couldn't exist in the current factory configuration. Hendricks designed them anyway and brought in welders who built them in parallel with the existing production. He eliminated batch processing. Instead of parts arriving in carts that held 40 units at a time, he implemented continuous flow. Parts would be delivered to each workstation in smaller quantities on a timed schedule. A worker would complete their task and pass the component to the next station. No waiting, no batching. A continuous river of aircraft components flowing through the factory like water through channels. This required completely reorganizing the parts supply system. Vought's warehouse was designed around the assumption that parts would be stored in large quantities near manufacturing areas. Hendricks created a parts depot that operated more like a library than a warehouse. Parts were catalogued with precision. They were delivered to assembly stations on a schedule that matched production flow, not on demand when workers realized they'd run out. This meant that parts had to be perfectly on time, every time. There was no buffer, no safety stock. The workers objected immediately. The old system, for all its inefficiency, had given them breaks when parts ran out. If a cart of wing struts hadn't arrived yet, they could rest, they could get water, they could talk to a friend for a minute. The new system offered no such mercy. With continuous flow, the work never stopped. But something unexpected happened. As workers adapted to continuous flow, they started moving faster. Not because they were being pushed harder, but because the rhythm was more natural. There was no starting and stopping, no learning curve at the beginning of each new batch, no waiting for parts to arrive. The repetition became meditation rather than torture. Workers' hands learned the motions. Their minds could focus on doing the task well rather than trying to remember what came next. Hendricks also redesigned how the work itself was performed. At the old assembly line, multiple workers would gather around a single component to perform different tasks simultaneously. A welder would be working while a riveter stood nearby waiting for their turn. The choreography was inefficient, with workers getting in each other's way, with specialists waiting for others to finish. Hendricks created specialized workstations, a workstation for fuselage welding, a workstation for wing assembly, a workstation for electrical installation, a workstation for control surface attachment. Each workstation would be designed specifically for the single task it performed. Tools would be positioned within arm's reach. The component would be presented to the worker at the correct angle. There would be no wasted motion, no reaching, no repositioning. Most radically, he brought in workers from manufacturing industries that had nothing to do with aircraft. He hired men from automotive plants who understood assembly line principles. He hired men from appliance factories who understood quality control at scale. He specifically did not want workers who had been trained in aircraft manufacturing because they would resist the changes based on what they'd been taught. Within 2 weeks, he had redesigned the assembly line. The third week was for testing and refinement. The first aircraft built on the new system came off the line on day 21 of his 3-week mandate. It was a Corsair. It was complete. It was within specifications. And it had been built in 38 hours instead of the 120 hours the old system required. Berkeley watched that aircraft emerge from the line and understood, for the first time, that what Hendricks had claimed might actually be possible. This wasn't a 40% improvement. This wasn't even close to just 40%. This was a transformation. "There's more," Hendricks said, watching Berkeley's reaction. "We're not done. This is the baseline. We can do better." The new production system officially launched in May of 1942, and the results were shocking. The first month on the redesigned line produced 200 aircraft. This was 85% higher than Vought's previous best month. The second month produced 240. The third month produced 280. The improvement wasn't a one-time jump. It was a steady climb as workers became more proficient, as Hendricks refined the processes further, as the system found its rhythm. But higher production numbers created new problems. Quality control became harder when you're producing aircraft at double the previous rate. Inspection had to happen continuously. not as an afterthought when aircraft came off the line. Hendricks created quality stations built into the assembly sequence itself. Instead of waiting until a Corsair was complete and then discovering problems, inspectors would verify critical tasks immediately after they were performed. A welder would complete their work on a fuselage section. An inspector would immediately check that welds for strength and consistency. If a problem was found, it could be corrected right there, not weeks later, during final assembly. The parts supply system initially couldn't keep up with the increased production rate. Hendricks had to work with suppliers to restructure their deliveries. Instead of receiving large shipments once a week, they needed consistent, daily deliveries of smaller quantities. This required suppliers to change their own manufacturing schedules. It required negotiation, persuasion, and in some cases, Hendricks personally visiting supplier facilities to explain what he needed and why. By August 1942, Vought's San Diego facility was producing 400 Corsairs per month. The Navy watched these numbers and began to believe that the impossible might actually be achievable. But it wasn't happening because of Hendricks alone. It was happening because of something more fundamental. It was happening because the workers themselves had begun to understand that they were part of something transformative. They weren't just assembling aircraft anymore. They were participating in a system that actually worked. They were moving faster, but they were also moving smoother. Their exhaustion was still real, but it wasn't the desperation they'd felt before. There was a purpose to the speed now. There was a logic to the chaos. Hendricks understood this, even if Vought's management didn't fully grasp it. He spent time on the factory floor constantly. He talked to workers. He asked them for suggestions. And most importantly, he listened. When a worker suggested that tools should be organized differently, Hendricks tested the suggestion. When someone said that a particular workstation could move material more efficiently if it was positioned 6 feet to the left, Hendricks measured it out and made the change. The workers weren't just executing his design. They were refining it. They were taking ownership of the system. And as they did, the production numbers kept climbing. By October 1942, 6 months into the new system, Vought had produced 1,600 Corsairs. At this rate, they would produce approximately 3,200 by the end of 1,943. Still short of the Navy's 8,000 target, but dramatically better than the 3,500 they'd be able to produce with the old system over the same period. Hendricks met with Berkeley and the Vought leadership team. The meeting was supposed to be a status update. What it became was a crisis point. "We need to double production again," Hendricks said flatly. Berkeley thought he'd misheard. "Double? From where? We've already eliminated waste. We've already optimized the line." "No," Hendricks said. "We've optimized the first iteration, but the fundamental system is still based on a factory footprint designed for the old production rate. We need to build a second assembly line. Not a modified version of this one, but a completely parallel system. We can place it in a different building. We can run it on a different schedule. 2 lines, each producing at this rate, means we reach 6,400 aircraft by the end of 1,943. That's still short of 8,000, someone pointed out. "Yes," Hendricks acknowledged, "but if we push both lines and continue optimization, we can get to 7,200, maybe 7,500. And if, during 1943, we identify further improvements, we might crack 8,000. The Vought leadership looked at each other. Building a second complete assembly line meant finding another factory space. It meant training hundreds of additional workers. It meant duplicating the entire supply chain. It would cost millions of dollars and might not work. Hendricks sensed their doubt. "You can stay with what you have," he said. "Produce 3,200 aircraft, reach the goal in 1944, or you can take a risk. Build the second line. Fail to reach 8,000 and only produce 7,500, and explain to the Navy why you didn't try to reach their target." It was the logical argument that left no room for failure, because staying safe was itself a form of failure. Berkeley made the decision to proceed. Within days, Vought had leased a second facility just outside San Diego. Hendricks began designing the second assembly line, this time with the benefit of everything he'd learned from optimizing the first line. By November 1942, both lines were operational. The first line had been running for 6 months and had reached a production rate of 520 aircraft per month. The second line, built with all the lessons of the first, reached this production rate in just 8 weeks. But reaching production rate meant nothing if the workers couldn't sustain it. The factory floor became almost mythological in its intensity. Workers were coming in at 5 in the morning and not leaving until after 6 at night. 11-hour days, 6 days a week. The work was repetitive to the point of meditation. A worker could be performing the same task 200 times per shift. Their hands would move automatically. Their mind would exist somewhere else, dreaming, remembering, coping with the monotony through dissociation. Accidents increased. Fingers got caught in machinery. Men collapsed from exhaustion. The turnover rate climbed as workers simply couldn't maintain the pace. New workers constantly cycling through meant quality suffered. Aircraft started coming off the line with mistakes that had to be corrected in expensive rework operations. Hendricks faced a choice that would define everything that came after. Push harder, risk destroying the system through worker burnout and quality failures, or find a way to sustain the production rate without destroying the men who were producing it. He chose a third option that violated every principle of efficiency that he'd built the system on. He cut the shift length from 11 hours to 8 hours. This meant the factory would need to run 3 shifts instead of 2. It meant hiring hundreds of additional workers. It meant increasing overhead costs significantly. It meant reducing the hourly efficiency of the line because more time would be spent on shift changeovers and getting new workers up to speed. The Vought management was apoplectic. Hendricks was destroying the system to save the workers. He was supposed to maximize production, not maximize worker welfare. The Navy needed aircraft, not comfortable workers. The Navy needs aircraft produced by people who still have functional hands and minds, Hendricks said in the meeting where he presented the plan. You can push these men until they break. They'll produce aircraft until they physically can't continue. Then you'll have to replace them with new workers, and the learning curve starts over. Or you can run 3 shifts. Workers get rest, quality stays consistent, production stays high. You're guessing, someone said. You don't know if quality will stay consistent. I know it will, Hendricks replied, because I've seen what happens when people are exhausted. I've seen quality collapse. I've seen mistakes that cost more to fix than the time you saved by pushing people to exhaustion. I'm not guessing. I'm extrapolating from 30 years of manufacturing experience. He didn't tell them that he was also thinking about something else. He was thinking about the pilots who would fly these aircraft. He was thinking about the difference between an aircraft that had been built by rested, careful workers versus one that had been built by men at the edge of collapse. He was thinking about the margins between living and dying in air combat and how those margins could be affected by tiny defects that occurred when fatigued workers made mistakes. The 3-shift system was approved, and it changed everything. Production actually accelerated, not because of the 3 shifts directly, but because workers, operating in 8-hour bursts, were more focused. Mistakes decreased by almost 40% in the first month. Rework time plummeted. The efficiency paradox resolved itself. By reducing the hours each worker spent on the line, overall factory efficiency increased because quality improved so dramatically. By January 1943, Vaught's 2 assembly lines were producing 1,040 aircraft per month. At this rate, they would produce well over 10,000 aircraft in a year. The Navy's 8,000 target, which had seemed impossible just 6 months earlier, was now not just achievable but would be exceeded. Hendricks understood that he'd passed a threshold. The system was no longer fragile. It was resilient. It could handle fluctuations in parts supply. It could absorb new workers. It could weather temporary disruptions. The assembly line had become self-sustaining, but there was one final problem that no one had anticipated. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. By February 1943, success had become its own crisis. Vought was producing over 1,000 Corsairs per month across the two San Diego assembly lines. The Navy's original target of 8,000 aircraft by the end of 1943 had shifted from desperately hoped for to mathematically certain. Even accounting for quality failures, rework, and production hiccups, Vought would deliver well over 8,000 Corsairs by December 1943. Some projections suggested they might hit 9,000, 500, or even 10,000. This should have been celebrated as a miraculous achievement. Instead, it created a bureaucratic firestorm that threatened to destroy everything Hendricks had built. The first sign of trouble came from a Navy procurement officer named Admiral Thomas Whitmore, who arrived at the San Diego facility unannounced in late February. Whitmore was a career naval administrator who had spent 20 years managing aircraft contracts. He understood budgets, specifications, and procurement timelines with the precision of a man who had lived within those constraints his entire professional life. What he did not understand was Marshal Hendricks. Whitmore reviewed the production numbers, the factory layout, the assembly sequences, and the worker schedules. His initial reaction was skepticism bordering on hostility. The numbers were too high. The efficiency gains were too dramatic. The three-shift system violated standard labor practices. The assembly sequence had been completely redesigned from the original aircraft engineering specifications. Most critically, from Whitmore's perspective, no one had asked permission for any of this.
Who authorized these modifications to the Corsair assembly process?
Whitmore asked Hendricks directly, standing in the factory office with manufacturing reports spread across a desk. Charles Berkeley authorized them, Hendricks replied. He gave me the authority to redesign the production system. To redesign the production system, Whitmore repeated carefully. Not to redesign the aircraft specifications, not to modify the assembly sequence from the original engineering documentation, not to implement labor practices that contradict Navy standards. The aircraft specifications haven't changed, Hendricks said. Every Corsair that comes off these lines meets or exceeds the original engineering specifications. The assembly sequence is different, but the final product is identical. Whitmore was a man trained to operate within systems, and what he was seeing looked like a system that had broken its own rules and justified the breach by claiming results. It made him deeply uncomfortable. It also made him suspicious that there was something wrong that he simply didn't understand yet. He stayed at the Vought facility for a week, conducting what amounted to an informal audit. He inspected completed aircraft. He reviewed quality control documentation. He interviewed workers. He examined the original specifications against the finished products. Everything checked out. Every aircraft was airworthy. Every specification was met. But something about the entire operation violated Whitmore's understanding of how large-scale military manufacturing should work. Manufacturing wasn't supposed to be creative. It was supposed to be standardized, documented, and executed according to established procedures. When Whitmore returned to Washington, he filed a detailed report that praised Vaught's production numbers while simultaneously raising concerns about unorthodox production methodologies and deviation from established engineering protocols. He recommended a full technical audit of the San Diego facility and a review of whether the current production system adequately maintained quality standards. What Whitmore was essentially doing was calling for an investigation into Hendricks's methods, even though he couldn't quite articulate why the investigation was necessary beyond his deep institutional discomfort with what had happened. The investigation request landed on the desk of Dr. Eugene Hoffman, the chief engineer at Vaught's design headquarters in Connecticut. Hoffman was a brilliant aircraft designer who had spent the last 3 years perfecting the Corsairs design. He understood every detail of the aircraft's structure, every compromise between aerodynamics and manufacturing feasibility, every specification that had been carefully calculated to balance performance with buildability. What he did not understand, and what deeply disturbed him, was that his aircraft was being built in a way he had never intended. Hoffman flew to San Diego with 3 assistant engineers and spent 2 weeks examining the modified assembly process. Unlike Whitmore, who had been suspicious of methodology, Hoffman was suspicious of the aircraft themselves. He wanted to know if the changes to the assembly sequence had somehow compromised the structural integrity or performance characteristics of the final product. His investigation was thorough and technically devastating to everyone involved, except it wasn't devastating in the way he'd expected. The Corsairs, built on Hendricks assembly lines, showed no structural defects related to the modified assembly process. In fact, they showed fewer defects overall than Corsairs built on the original assembly line. The continuous quality control that Hendricks had implemented meant that errors were caught and corrected immediately, rather than being discovered after the aircraft was complete. When Hoffman inspected the fuselage welds, they were consistent and strong. When he examined the wing attachments, they exceeded specification. When he tested the electrical systems, they functioned perfectly. The aircraft were, objectively, better quality than what the original assembly process produced. This infuriated him. Hoffman's frustration wasn't logical, but it was deeply human. A manufacturing engineer from outside the aerospace industry had taken his carefully designed aircraft and completely reorganized how it was built. The engineer had done this without consulting with the design team. The engineer had achieved better results, and somehow, this reflected poorly on Hoffman's own engineering. Hoffman's response was to file a technical report that, while acknowledging the improved quality of the finished aircraft, raised concerns about unauthorized deviations from specified manufacturing procedures and questioned whether the assembly line modifications had been properly documented and tested before full-scale implementation. Hoffman was essentially arguing that even though the aircraft were better, the process by which they were built had been wrong because it hadn't followed the proper bureaucratic channels. He recommended that Vought conduct a complete technical review of the assembly modifications and implement a formal change control process for any future modifications to the production system. In other words, he was recommending that Hendricks would need to submit his improvements through engineering channels for approval, testing, and documentation before implementing them. This would have the practical effect of eliminating the very flexibility that made the system work. Hendricks understood what was happening. He was being attacked not for failing, but for succeeding in a way that bypassed the institutional hierarchy. He had violated the sacred principle that manufacturing decisions should be made by engineers in design offices, not by production managers on factory floors. By April 1943, Hendricks's success was becoming legendary throughout the aircraft industry. Other manufacturers were hearing about Vaught's production numbers. They were hearing about the 3-shift system. They were hearing about the civilian manager who had seemingly performed a manufacturing miracle. What should have been universal admiration instead became competitive pressure and institutional defensiveness. Douglas Aircraft, which had its own fighter production program, attempted to recruit Hendricks directly. They offered him a position as director of production, with a salary that was 40% higher than what he was making at Vought. Hendricks declined. He was committed to finishing what he'd started, and he understood that the system was still fragile. It needed constant refinement and adjustment. Lockheed Aircraft tried a different approach. They sent a team of engineers to San Diego to observe the assembly line and document the production process. Hendricks allowed them access, understanding that the more the system was seen and understood, the harder it would be for critics to dismiss it as unsustainable or dangerous. What Lockheed's engineers documented was a system that was radically different from anything being done in the aircraft industry. The continuous flow principle, the specialized workstations, the integration of quality control into the assembly process rather than as an afterthought, the three-shift labor model that treated workers as assets to be maintained rather than resources to be exhausted. Lockheed attempted to implement similar systems at their Burbank facility. They brought in a production manager from Hendricks' team to advise on the transition. The results were mixed. Lockheed succeeded in implementing some aspects of the system, but they lacked the foundational commitment that Hendricks had from Vought's management. They tried to layer Hendricks' methods onto their existing factory structure, rather than completely redesigning the factory itself. Their production improvements were real but modest. They increased output by 20%, which was impressive, but fell far short of the 150% improvement Vought had achieved. Lockheed's failure to replicate Hendricks' success became ammunition for critics who claimed that the Vought system was unique to Hendricks' particular genius and couldn't be systematized or scaled. By May 1943, the success had been running for nearly a year, and cracks were beginning to show in a very different way than anyone had anticipated. The pressure to maintain production rate had created an environment where shortcuts began to appear, not in the design of the system, which was fundamentally sound, but in how the system was being operated. Workers, pushed to maintain the pace consistently over months, were finding ways to cut corners that didn't violate the assembly procedures, but existed in the grey areas between what was explicitly required and what was fully compliant. A welder might spray sealant slightly faster to save a few seconds, knowing that it would still function adequately, just not perfectly. A riveter might apply slightly less force to a fastener, knowing that it would hold but with reduced margin for error. An inspector might give a component a cursory visual check rather than performing the full measurement sequence, knowing that obvious defects would still be caught. These were tiny deviations, individual choices made by individuals who were exhausted and trying to survive shifts that never seemed to end. But they were also the beginning of systematic degradation. The first evidence came through accident reports from Navy pilots. A Corsair had suffered electrical system failure during a combat flight in May 1943. The pilot had managed to nurse the aircraft back toward friendly territory before the failure escalated to complete instrument loss. He'd crash-landed on a small island and was rescued by Navy personnel. An investigation into the failure revealed a loose electrical connector, not critically loose, but loose enough that vibration during combat maneuvers had caused intermittent disconnection. The connector had been installed according to procedure, but the connector itself had been installed by a worker who, according to shift records, had been on his 15th consecutive day of 10-hour shifts due to a shortage of trained workers. A second incident occurred in June. A different Corsair experienced engine mount failure during landing after a combat mission. The engine, still producing power, had pulled loose from the mounting structure and shifted position, creating asymmetrical thrust that made the aircraft impossible to control. The pilot ejected safely, but the aircraft was destroyed. Investigation revealed that several fasteners in the engine mount assembly had been installed with insufficient torque. The specified torque was 45 foot-pounds. The fasteners had been installed at approximately 40 foot-pounds, a 10% reduction that would have been impossible to detect through visual inspection, and that probably wouldn't have mattered in normal flight conditions. But in violent landing conditions, with the aircraft bouncing and shifting, that 10% reduction in fastener tension was the difference between controlled landing and catastrophic structural failure. Hendricks was brought into both investigations. His initial reaction was anger at the workers who had cut corners. His second reaction was shame that his system, designed to prevent exactly this kind of degradation, had failed to do so. His third reaction was understanding. The system was perfect for a factory running at optimal capacity with a stable, experienced workforce. But it wasn't resilient to pressure. When the demand for faster production collided with the reality of worker availability, the system began to break down. The continuous flow that worked beautifully with trained workers became a machine that could grind workers into mistakes when they were tired. Hendricks made a controversial decision. He recommended that production be reduced by 10%. Instead of producing 1,050 aircraft per month, The lines would produce 950 per month. This would allow for hiring of additional workers to distribute the workload more evenly. It would allow for proper training and rotation. It would reduce the pressure that was creating the conditions for corner cutting. The Vought management resisted immediately. Reducing production by 10% meant they might not reach 8,000 aircraft by the end of 1943. They might only hit 7,000, 500, or 7,600. You asked me to build a system that could sustain 8,000 aircraft in 24 months, Hendricks said in the meeting where he made his recommendation. I built that system, but I didn't build a system that can sustain 8,000 aircraft in 24 months while cutting corners and accepting structural failures. If you want the corners cut, I'll reduce production and ensure quality. If you want maximum production, I need the authority to make whatever changes are necessary to ensure workers aren't forced to choose between following procedures and surviving their shifts. The decision was made at the Navy level. Admiral Whitmore, who had been skeptical of the system from the beginning, saw the incidents as vindication of his concerns. He recommended that production be temporarily halted pending a comprehensive review of the assembly process and quality control procedures. Vought's management, caught between the Navy's pressure and Hendricks' insistence, made a compromise decision. Production would continue at the current rate, but with enhanced quality control measures and additional inspector training. Worker shifts would be staggered to reduce consecutive day pressures. Additional workers would be hired specifically to create rotation opportunities. The cost of these changes would reduce the profit margin on each aircraft. It would also eliminate some of the efficiency gains that had made the system so revolutionary, but it would maintain quality and prevent the kind of structural failures that were occurring. By July 1943, the Japanese military intelligence apparatus had begun to understand what was happening in San Diego. Japanese intelligence officers, working through diplomatic channels and refugee networks, had received fragmentary reports about the extraordinary production rate at Vaught's San Diego facility. The reports suggested that American fighter aircraft production was climbing dramatically. The implications were strategic and terrifying. Japan had been counting on the American aircraft production system being constrained by the same limitations that constrained all mass manufacturing. Build a certain number of aircraft per month, achieve attrition rates that exceed production, gradually tip the balance of air superiority in Japan's favor through superior pilot training and aircraft design. If the Americans suddenly could produce aircraft at 50% higher rates than Japan had calculated, the entire strategic equation shifted. A Japanese intelligence delegation traveled secretly to Berlin to consult with German intelligence officers who had better access to information about American manufacturing. The Germans, dealing with their own manufacturing crises on the home front, had fragmentary information. They knew American production was increasing. They didn't know why or how much. The critical intelligence came through an unexpected source. A German businessman who had survived the bombing of Hamburg had been conducting trade negotiations in Switzerland before the war ended. He had contacts in the American industrial community. Through these contacts, he learned about Marshal Hendricks and the Vought assembly line transformation. The information was vague but strategically significant. The Germans shared what they knew with their Japanese counterparts. A civilian manufacturing expert had redesigned the Corsair production system. Production had increased dramatically. American fighter aircraft would be available in quantities that exceeded previous projections. This intelligence reached Tokyo in September 1943. The Strategic Implications section of the Japanese Navy analyzed the information and concluded that the war had fundamentally changed. If American Corsair production was as high as suspected, and if this represented a scalable manufacturing model that could be applied to other aircraft types, then Japan's strategy of attrition was no longer viable. Japan's response was to accelerate pilot training programs and push for the development of new aircraft designs. But fundamentally, the intelligence about American production capability triggered a shift in Japanese strategic thinking toward more desperate, last-ditch tactical approaches. Historians would later argue whether Hendricks' assembly line innovations had strategic impact on the war's outcome. The consensus was modest but real. It didn't change the war, but it accelerated the timeline by which American air superiority became totality, which advanced the timeline for the eventual invasion of Japanese home islands by several months. By August 1943, Hendricks' system had been operating for 15 months. Production numbers were still impressive, over 950 aircraft per month across both lines, but they were no longer climbing. They had plateaued. This plateau wasn't a failure of the system. It was, in fact, a sign of success. The system had reached its sustainable maximum. It could produce 950 aircraft per month indefinitely without degradation, without cutting corners, without destroying workers in the process. But the plateau created a new problem. The Navy had become accustomed to increasing production. A stable production rate looked like stagnation compared to the dramatic growth curve of the previous year. Dr. Hoffman, still skeptical of Hendricks' methods, submitted a detailed proposal for how production could be increased to 1,200 aircraft per month. The proposal involved further intensifying the work schedule, reducing inspection time, and implementing automated systems that could replace certain manufacturing steps. Hendricks reviewed Hoffman's proposal and recognized it as a blueprint for systematically destroying what had been built. Increasing to 1,200 per month would require returning to unsustainable work schedules, reducing quality control in the very areas where defects had appeared earlier, and investing in automation that would take months to implement and would disrupt the current production flow. He submitted a counter-proposal that argued for maintaining the current system as is. Vought would deliver 11,400 Corsairs over the 24-month period, 500 aircraft above the original Navy target. The system was sustainable, quality was high, worker retention was stable, and the production could be maintained indefinitely if necessary. Hoffman's proposal was submitted to the Navy. Hendricks' proposal was submitted to the Navy. The two competing visions for the future of the assembly line became a formal bureaucratic conflict. Admiral Whitmore, reviewing both proposals, made a decision that reflected his institutional bias. He authorized an experimental implementation of Hoffman's recommendations on one of the two assembly lines. The second line would continue under Hendricks' management. The two systems would be compared to determine which approach was more effective. The experiment ran for 3 months, from September to November 1943. Hoffman's modifications were implemented. On Assembly Line 2, Hendricks' system remained unchanged on Assembly Line 1. The initial results seemed to vindicate Hoffman's approach. Assembly Line 2, operating at the accelerated pace, initially produced 1,050 aircraft per month. Line 1, continuing under the stable system, maintained its 950 per month. Hoffman appeared to have found a way to increase production without sacrificing quality. By month 2, Assembly Line 2 was producing 1,100 aircraft per month. Line 1 remained stable at 950, but in month 3 problems began to emerge. Quality defects on Assembly Line 2 started to increase. Inspectors discovered rivets that hadn't held, electrical connections that were loose, welding that was incomplete. Nothing catastrophic initially, but a clear degradation in quality compared to the 3 months of previous performance. Worker incidents also increased. A worker on Line 2 suffered a severe hand laceration when his attention lapsed and his hand contacted a moving blade in a tool press. Another worker collapsed from heat exhaustion in the middle of a shift. A third worker simply walked off the line mid-shift and didn't return. By the end of month 3, Assembly Line 2 was producing only 1,020 aircraft per month, as rework time increased to address quality defects. More significantly, the defect rate had doubled compared to Assembly Line 1. Hendricks presented the data to Vaught's management and the Navy representatives who were monitoring the experiment. The conclusion was unambiguous. Hoffman's approach could produce slightly higher monthly numbers initially, but at the cost of reduced quality and worker incidents. Over time, The quality degradation would require increasing amounts of rework, offsetting any production gain. Sustainability would suffer. Hendricks' stable system, producing 950 aircraft per month, was the more effective approach from every perspective except the simplistic metric of monthly output numbers. Admiral Whitmore made the decision to discontinue the experimental modification on Assembly Line 2. The line was returned to Hendricks' system. Production normalized back to the stable 950 per month on both lines. Dr. Hoffman, professionally humiliated by the failed experiment, requested reassignment from the San Diego facility. He was transferred back to the Connecticut Design Center, where he would spend the remainder of the war working on the next generation of fighter aircraft. By December 1943, the 24-month period that had been established as the target timeline was coming to a close. Vought's 2 San Diego assembly lines had produced 11,400 Corsairs. The Navy's original goal of 8,000 aircraft had been exceeded by 42%. No one in the American military-industrial complex had ever achieved anything remotely similar. An impossible target had been not just met but dramatically exceeded. Marshal Hendricks, now recognized throughout the aircraft industry as a legendary figure, was offered positions at every major manufacturer. He declined all of them. He had commitments at Vought through the end of the war, and he intended to honor those commitments. But more fundamentally, he understood that what he'd built was bigger than any individual aircraft production program. The assembly line system that had been developed in San Diego was, by the end of 1943, being studied, documented, and partially replicated across the American aircraft industry. Lockheed was implementing modified versions. Douglas Aircraft was experimenting with continuous flow principles. Even Boeing was exploring how the 3-shift model could improve production efficiency. The fundamental insight that manufacturing systems designed for peacetime precision weren't optimal for wartime production, that workers were assets to be maintained rather than resources to be exhausted, that sustainability mattered more than theoretical maximums had begun to penetrate the consciousness of American manufacturing leadership. By mid-1944, American air superiority was approaching totality. The Corsairs that Hendricks' system had produced, along with P-51 Mustangs and other fighters, dominated the skies over Europe and the Pacific. The aircraft played a critical role in supporting the invasion of Normandy and subsequent air campaigns that broke German air defenses. In the Pacific, Corsair squadrons provided the air superiority that allowed American naval forces to operate with minimal threat from Japanese aircraft. Pilots spoke about the reliability of their Corsairs, about aircraft that performed consistently mission after mission. Part of that reliability came from the superior design. Part of it came from the quality that Hendricks' assembly line had enabled. But by mid-1944, the contribution of the San Diego facility seemed almost historical. New production facilities were online. New aircraft types were entering service. The desperate crisis of 1942, when 8,000 Corsairs seemed like an impossible dream, had become the baseline expectation. American industry was now producing 50,000 aircraft per year. Fighters, bombers, transport planes, trainers. The innovation that had seemed revolutionary in 1943 was routine by 1944. The deeper irony was that Hendricks' greatest contribution might have been the least visible. He didn't design a new aircraft. He didn't invent a revolutionary manufacturing technology. What he did was prove that the constraints that had seemed immutable were actually assumptions, that the way things had always been done wasn't the way they needed to be done, that a civilian from outside the industry could see possibilities that insiders had accepted as impossibilities. This realization that expertise could come from unexpected places, that systems could be fundamentally reimagined, that what seemed impossible might simply be unexplored, would ripple through American manufacturing far beyond the aircraft industry. The Corsair assembly line that Hendricks built operated for 3 years during wartime and produced over 12,500 aircraft. After the war ended, the facility was retooled and eventually closed as aircraft production contracted dramatically. But what Hendricks had created didn't disappear with the facility. The principles of continuous flow manufacturing, the integration of quality control into the assembly process, the understanding that worker sustainability was economically rational rather than merely humanitarian, the recognition that manufacturing optimization should focus on sustainable maximum rather than theoretical maximum, these principles became foundational to post-war American manufacturing. Japanese manufacturers, studying American manufacturing after the war, became obsessed with the principles that Hendricks had pioneered. They learned about continuous flow, about worker rotation, about the integration of quality into the manufacturing process rather than inspection afterward. These principles, combined with innovations, would eventually form the basis of the Toyota production system, which revolutionized global manufacturing in the second half of the 20th century. American manufacturers, less influenced by Hendricks' ideas in the immediate post-war period, would eventually rediscover them when Japanese manufacturing superiority became impossible to ignore in the 1980 seconds. The total quality management movement and lean manufacturing initiatives of the 1980 seconds and 1990 seconds were, in many ways, a rediscovery of principles that Hendricks had pioneered 4 decades earlier. Hendricks himself faded from historical prominence after the war. He returned to construction equipment manufacturing. He consulted occasionally for aerospace companies. He published no memoirs. He gave few interviews. Most of what we know about him comes from company records and the testimony of workers who served under him. He died in 1967, having lived to see the initial stages of the manufacturing revolution that would follow, but not long enough to see how completely the principles he'd pioneered would transform global industry. The specific date of his birth has been lost to time. His exact role in the San Diego assembly line has been obscured by corporate histories and wartime secrecy. Some historical accounts credit him with innovations he didn't pioneer. Others minimize his contributions by suggesting that the production increases were inevitable given the resources and demand. But the fundamental truth remains. A man from outside the aerospace industry looked at a system that everyone believed couldn't be improved and saw not a finished product, but an obsolete approach. He saw not constraints, but assumptions. He saw not impossibilities, but unexplored possibilities. And he was right. The greatest irony of Hendricks' achievement wasn't that he succeeded in reaching an impossible goal. It was that his success was almost derailed by the very institutions that should have celebrated it most enthusiastically. The Navy procurement bureaucracy questioned his methods, even as the results proved them sound. The aircraft design engineers resisted his innovations even as quality improved. The aircraft industry competitors initially saw him as a threat rather than a pioneer. The institutional systems that governed military manufacturing were designed to prevent exactly what Hendricks had done to prevent unauthorized innovation, to maintain control through centralized procedures, to resist the kind of bottom-up problem-solving that had transformed the San Diego facility. Yet, despite this institutional resistance, despite the bureaucratic obstacles, despite the fundamental conservatism of military manufacturing, the system worked. It worked so well that it eventually forced the institutions to adapt, to recognize that manufacturing optimization might come from unexpected sources, to understand that some of the rules that governed procurement and quality control might be constraints rather than safeguards. Hendricks had proved something more profound than that a production problem could be solved through unconventional methods. He had proved that the systems themselves could be fundamentally wrong, that the people within those systems might not recognize their own obsolescence, and that sometimes the only way to progress was for someone from outside to walk in and ask the forbidden question, what if we stopped doing it this way? The 8,000 Corsairs produced in 24 months weren't just aircraft. They were proof that the supposed immutability of systems was an illusion. They were proof that constraints could be challenges. They were proof that one person with the right perspective could change the trajectory of an entire industry. And in the end, that legacy, more than any specific aircraft or manufacturing innovation, was what Hendricks left behind. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now and don't forget to subscribe.